Boa tarde. So today we have Francesca Pinna. She has been visiting Brazil already for since last week.
Couple of weeks more.
Couple of weeks more. Yeah. So we recently organized this AU symposium on stellar populations in Paraty in honor of Professor Beatriz Barbuy, and Francesca also attended this symposium, and she has been working on stellar populations on using nearby galaxies, and mainly IFU spectrograph. And she, before her current position at the Instituto de Astrofísica de Canarias in Spain, where she holds a prestigious Maria Curie Fellowship, she did a postdoc at the Max Planck Institute for Astronomy for 4 years. And today she will speak about deciphering the origin of thick disks with their stellar populations.
Thank you very much, Jorge, for the very nice introduction. So hello, everyone. I would like to thank also Paula Coelho, who is probably not here yet because of the traffic in Sao Paulo, but she's arriving, I'm confident, because she's hosting me here, and it's been very nice to visit you here at this institute, giving me this opportunity to give this seminar, but also to chat with several of you here this week. So I'm in the office 311. Feel free to pass by my office if you want to discuss anything about my talk or your science, your results. I would be very happy to chat with you. And also feel free to interrupt me at any point during my talk if you have any questions. So yes, I will talk about stellar populations of nearby adjoint galaxies, and I will try to show you how this can be used to understand a little bit better the origin of thick disks. I will also try to convince you that thick disks are very important, they are very interesting, and they can help you help us to understand better the evolution of these galaxies. So I will start with the Hubble sequence. From the very beginning, I guess most of you are familiar with this sequence, but just in case, this is one of the ways we can classify galaxies according to their morphology in this case. And in this talk, we will focus on these galaxies, which are located here in the Hubble sequence. So here we have elliptical galaxies, and here we have lenticulars and spiral galaxies. So we will talk about galaxies that have a prominent disk, either without a clear spiral structure, like lenticular galaxies, or like with a clear spiral structure, spiral galaxies. So I will try to summarize the results that we have for thick disks in these types of galaxies, going from early type galaxies to later type galaxies. So from the left to the right of the Hubble sequence. So if we observe these galaxies when they are projected adjoint in the sky, this can actually help us to see to analyze their vertical structure. So we can see there is a bright thin structure in the midplane here, which is the thin disk, where we have most of the star formation going on, most of the gas, and where we actually also live. This is actually a schematic view of the Milky Way, and the sun is actually here. But then we have also another structure which is thicker and which is fainter, which is called the thick disk. So the term thick disk, so a little bit of history here. This term was started to appear in the late 70s when Barstein understood that it was necessary to add the second disk component to fit vertical surface brightness profiles of adjoint galaxies. In particular, this happened with 5 lenticular galaxies. And he understood that it was needed to add a second component with a larger scale height, which was actually called the thick disk because it was thicker. So at the beginning, the thick disk was defined in a pure geometrical way. I will go back in a couple of slides to this definition because it is also what we usually use in external galaxies when they are seen adjoint. So a bit later on, the thick disk was also identified in the Milky Way. But in this case, we could extract spectroscopically the properties of individual stars, and therefore it was possible to identify some key properties of the stars of the thick disks. So the thick disks were found to have stars which were very old, metal poor, especially older and more metal poor with respect to the stars in the thin disk, and kinematically hotter. Here, by kinematically hot, we mean with higher velocity dispersions. And a little bit later on, it was also found that the stars of the thick disk were alpha enhanced, so enhanced in alpha elements. Similar properties were also later found in many external galaxies, although, well, we show in more or less in the second part of the talk that the thick disks are not necessarily always very old. So in the last studies, we are kind of challenging this general idea, but traditionally we believe that thick disks are old, metal poor, kinematically hot, and alpha enhanced. So given these properties, different definitions have been used for thick disks, especially in the Milky Way, where we can reconstruct the three-dimensional structure and where we can use different properties to define thick disks in different ways. However, in external galaxies, when they are seen edge-on, we just have the projection of the galaxies, and therefore we cannot do much more than using the fact that thick disks are actually thick or thicker than the thin disk, and use a geometric definition. So this means that we use a morphological decomposition. So we take a vertical surface brightness profiles, this is Z, and we fit them with two components. One which is brighter, dominating in the midplane, which is the thin disk, but from a certain height on, we have the second component dominating, which is the thick disk, so here. So basically our thick and thin disk will be defined in different regions, so the thin disk in the midplane region and the thick disk above and below. And the heights in which the thick disk starts to dominate will be different for different galaxies. So knowing what are the traditionally the properties of thick disk, we have said that they are in general hot, kinematically hot, but also old, metal poor, alpha enhanced. So what does this mean? This means that the stars were formed a long time ago. Because they are old, they were formed from a non-enriched gas, and also probably in a fast time scale, because the alpha enhancement is usually interpreted, especially in the context of thick disks, as a faster time scale. And this is related to the fact that supernovae type 2, which release most of the alpha elements, have shorter lifetimes than supernovae type 1a, which on the other hand release most of the iron peak elements. And therefore, when we form the first generations of stars, we have some enhancement of the alpha elements, and we have to wait a little bit more for supernovae type 1a to balance this enhancement with also iron peak elements. So these properties and these ideas actually tell us that thick disks were among the first structures to form in a galaxy, or at least their stars were formed at the very early stages of the formation and evolution of a disk galaxy. And therefore, they are very important because to understand the evolution of these galaxies, we need to understand also thick disks, which trace the early stages of the history of these galaxies. So how can we form thick disks? How can we form disks that have those properties that we have been talking about? So to explain these properties, so the fact that they are the stars in the thick disk are old, kinematically hot, metal poor, and alpha enhanced, there were several formation scenarios that were proposed in the literature, especially from theoretical studies, trying to explain these properties. One of them was the born-hot scenario. In this scenario, the stars of the thick disk were formed in a disk which was already thick from the beginning, and which formed high redshift. From a disk of gas, which was also thick and dynamically hot already from the beginning. But another possibility is that we first form a pre-existing thinner disk, and we heat this disk dynamically to make it thicker with time. And this dynamical heating can actually happen in a slow way, in a secular way, so with time, or in a fast way with violent mechanisms, such as, for example, mergers. I will go back to this in a second. But the third possibility, so these are kind of the three main families of scenarios that we have. A third possibility is an extragalactic origin, so the direct accretion of stars from satellites, which would form most of the mass of the thick disk. Okay, these were the scenarios proposed from, like theoretically. So what do we know from observations? What are the scenarios that are mostly supported by observations? It is natural to think about high-redshift galaxies, because if we want to understand the structure, which is made up of old stars that were formed a long time ago, we should go actually to high-redshift galaxies. And we have now these very nice recent studies of high-redshift galaxies so with the JWST. I'm citing here one in particular, which was actually submitted, so posted in the Astro-PH last month. And here I'm showing a sequence of galaxies with increasing redshift towards the right side, where we can see already that the morphology of galaxies evolved with time. So the main results of this paper, but also supported by previous papers, are that thick and thin disks, so a double disk structure, starts to appear quite early. Already 10 gigayears ago, we have some galaxies with a double disk structure. And I'm saying this because when we fit those vertical surface brightness profiles, like the one that I showed before, in most galaxies, let's say, we fit better with two components. But it is true that not all galaxies fit good, well with two components. There are some galaxies also in the nearby universe that are fitted best with only one component. And when we go to high-redshift galaxies, we see actually that a high redshift, most of the galaxies show a single disk structure. So the profiles are fitted best with one disk only. So most of the galaxies are single disks with some properties, with morphological properties that are more similar to thick disks, actually, to thick disks in the galaxies with a double disk structure. Furthermore, we have a transition to a double disk structure, which happens a bit later. And the time where this transition happens depends on the mass of the galaxy. So it is done in a downsizing fashion. This means that higher mass galaxies have this transition so from one disk to double disk structure earlier than lower mass galaxies. But the general idea here, which is important for this talk, is that thick disks apparently formed first than before the thin disk. So this is very much supporting more the Bornholm scenario than that dynamical heating that I mentioned before. Especially, this is basically ruling out the slow dynamical heating, because if this heating was low, we wouldn't be observing this kind of galaxies with only a single disk structure at high redshift. So the JWST studies are kind of new, as you know, but before that, in the last decades, we have been also doing some spectroscopy of very nearby galaxies, trying to do some galactic archaeology in external galaxies to go back in time and understand so reconstruct the history of thin and thick disks. So what do we know from spectroscopic observations? What are also the scenarios that mostly support by these observations? The very first studies, spectroscopic studies of thin and thick disk, actually the very first spectroscopic characterization of thick disks were done with the long slit. Actually, if we know what are the regions dominated by the thin disk in the midplane and the thick disk at a certain height, we can place two slits and we can measure the properties of the thin and the thick disk. So the very first series of papers was the Pioneer series by Yachim and Alcanton, in which they very much supported the accretion scenario. Remember, one of the scenarios was that most of the stars of the thick disks are actually coming from accreted satellites, because they found in the kinematics signs of counter-rotation. They found that it was actually necessary to account for a significant fraction of counter-rotating stars to explain the kinematics that they observed. And in fact, so from this counter-rotation fraction, they estimated that more than half of the thick disk was actually accreted, because of course not all the accreted stars counter-rotate. But after that, so of course they were trying to find like a universal formation scenario for all the thick disks. These were the very first studies, and a bit later on, some diversity also started to appear in the properties of thick disks. And Kasparov et al. Started to propose that the diversity actually meaning different formation scenarios and some more complexity. And this idea is very important because this is the idea that we also found in the most recent studies. So this was very nice, but of course long slit observations could not provide the vertical gradients because we could, in most studies we only had 2 slits. And vertical gradients are very important to understand which one of the scenarios is the most plausible. And also so long slit observations did not prove that the transition region between the thin and the thick disk, which is also very important to understand the connection and the transition from a single disk structure to a double disk structure in a galaxy. So to do this, we had to wait a bit more for integraph field spectroscopy, which actually provided very important pieces of information on the origin of thick disks. So from now on, I will try to summarize the results that we have from integraph field spectroscopy, and I will take you through the Hubble sequence from the left to the right. So from earlier type galaxies here in this region here to the latest type galaxies here on the right side, and I will start from lenticular galaxies. So talking about lenticular galaxies, I'm going to start with some work from my PhD thesis. This was the stellar population analysis of 3 lenticular galaxies at John in the Fornax cluster. And this was deep Muse data from the Fornax CD survey. And these are the 3 galaxies here, nicely at John. This is the central galaxy of the Fornax cluster. And this image is actually showing that the 3 galaxies are located at different distances from the cluster center. Keep in mind that this galaxy is the closest to the cluster center, FCC 170. I will show that its properties are a bit different from the other 2 galaxies. So what I did was to fit with a full spectral fitting technique, which is PPXF, the data cubes from Muse. So this technique basically take a set of stellar population templates and combines some of them to find the best combination of them to reproduce the original spectrum. So here I'm showing in black the original spectrum, and the PPXF best fit is the one in red. This is just an example, one of the pins. Something happens. Okay, we are back. So for these studies, I used the Manismo random variable version of the Miller's single stellar population models, because I also wanted to extract the Manismo random abundance, because as I said at the beginning, this is an important property for thick disks. So from the best fit combination of models, we can extract the stellar population properties. And I obtained these maps. So these are the 3 galaxies in different columns. I'm showing the transition between the thin and the thick disk with these 2 horizontal lines. So the thin disk is between the 2 lines, and the thin disk and the thick disk is above and below. And from top to bottom, I'm showing the age, metallicity, and Manismo iron abundance. So from a first glance, you can already see that in the age maps, we have some differences between the galaxy on the left side, which is FCC 170, and the other 2 galaxies. If you remember, I said that this galaxy was the one closest to the cluster center, and the differences are actually found in the thin disks of the galaxies, where this galaxy is actually overall very old. So here all the ages are orange and red colors. So this galaxy is basically overall very old, even in the thin disk, which is traditionally thought not to be so old. And actually in the other two galaxies, we see that the thin disks are much younger. So maybe I don't have time to go into the details, but we can discuss that this aspect a bit later. But this has to do with the fact that this galaxy on the left side actually has, so this one, is located in the descent region of the cluster. And this probably affected the formation of the thin disk. But yeah, this talk is basically focusing on the thick disks. So now let's try to focus on the thick disks. Actually, the thick disks in the three galaxies show a similar pattern, which is old ages. If you focus to these regions above and below the two horizontal lines, we see red colors and orange colors for the ages. So we are talking about very old ages. And we see blue colors for metallicity, which correspond to low metallicities. And we also have an alpha enhancement in the thick disks. So we have yellow, orange, red colors for the alpha enhancement. So basically these three thick disks follow the pattern that we expected, because this is the traditional idea that we have about thick disks. So an old metal poor alpha enhanced thick disk. And this is there any technical problem? Okay, good. This is very nice, but very interestingly, when we try to extract the star formation histories of these three thick disks, and this can be done with the weights that PPXF, so this full spectral fitting technique, assigns to the different models. So each SSP model corresponds to a combination of age, metallicity, magnesium over iron, and therefore to the mass weights, for example, given to each one of the models, we can reconstruct the distributions of the age, metallicity, and magnesium over iron. So here I'm showing one example of the one of the three thick disks, and this is the mass fraction for different ages. I'm also color coding the age bins according to the average metallicity in each one of the bins, and we can interpret this plot actually is in terms of time evolution if we go from older ages on the right side to the younger ages on the left side. The first thing that you notice here is that the star formation history is actually truncated very early. So we have very old stars in general. We don't have stars younger than more or less 7 giga-years. So very old thick disk stars. Furthermore, we have a main very old component, which is most of the mass, with some chemical evolution, with some increase in metallicity. So again, the blue colors are the lowest metallicities, and we go to some green here. But so this main component is kind of being quenched, or at least, yeah, you have this drop in the mass associated to each one of the age bins. We have an additional component, which is this younger component with a lower metallicity. And the way to explain this is to invoke accretion. So since you probably know that because of the mass metallicity relation, we form stars that have lower metallicities in galaxies that have lower masses. So the way to explain that we have for similar ages metallicity which are lower is to think that they were formed in lower mass satellite, and they were or more than one satellites, and they were later accreted. So basically, in these thick disks, so this is one of the galaxies, but we find a similar pattern in the three of them. We basically have a main population which is already very old and metal poor, which is the oldest one actually. But then we have this younger population which is more metal poor, for which we think accretion was responsible for that. So basically, we propose here complex formation of this thick disk with a main in-situ formation, but also an ex-situ contribution. So these were not the first studies on lenticular galaxies, actually, because in 2016 we had also a study from Sébastien Comeron et al. Of 1-0 galaxy in another galaxy cluster, and actually they found a similar pattern of age and metallicity to one of the galaxies. So the one that is overall very old. You remember the one with an old thin disk. They actually found also that this galaxy was overall very old. So here, this sorry about that. These black lines are identifying the transition between the thin and the thick disk. And they also found some differences in metallicity. So yeah, here the color scale is not the same. So that's why we see we don't see the same difference in color that we see in my maps. But they have lower metallicities in the thick disk than in the thin disk. So they also found a galaxy which is already overall very old, and thick disk which is much more metal poor than the thin disk. Unfortunately, they didn't fit also magnesium over iron, and they didn't accept the star formation histories, so we cannot kind of fully compare the results. But they proposed like a formation all at once of the thin and the thick disk together very early times. So this is for lenticular galaxies. What do we find in spiral galaxies now? It's natural to wonder if we find these properties also in the rest of these galaxies or not. So let's move a little bit to the right of the Hubble sequence. This was actually the very first study with interference spectroscopy, also by Comeron et al. This is 2015 paper, and this was done with VMOS, not with MUSE. You can actually see the poor spatial resolution compared to MUSE, of course, but it was the very first study and still very important. So the green lines are also indicating the transition between the thin and the thick disk, and we find, so the authors found in this galaxy also a thick disk which was very old. You can see red colors here for age, and low metallicities, compared to the thin disk which was much younger and more metal rich. So the authors propose here an internal variant origin, a high redshift for this thick disk which was very old and metal poor. Good. So now we'll show the results for NGC 5746, which is a very large and very massive SB galaxy, for which we had two MUSE pointings covering part of the disk. Actually, this was the work led by Marie Martig that we published in 2021. And we used a similar technique, actually this time also fitting the emission lines, because since we are moving towards the right side of the Hubble sequence, we are so here we start to find emission lines that need to be subtracted or masked to fit the absorption spectra. And these were the stellar population maps that we found. So again, we have age, metallicity, and magnesium over iron from top to bottom. And if we want to compare, so to analyze the regions that are dominated by the thick and the thin disk, we have to compare to the morphological decomposition, which is here on the right side. So the thick disk is this red region here, and the thin disk is this blue region. So if we compare this map with the stellar population maps, we actually realize that the thick disk is this old, metal poor, and alpha enhanced structure, while the thin disk, which is this region here, is much younger, metal rich, and close to Sorel values of alpha. Again, we find very old ages in the thick disk. So we are talking about again older than 11-12 gigayears. The thin disk is much younger, but we are still talking about like old ages. And this also, well, in the lenticular galaxies, we had values from 4, 5, 6 gigayears to older ages. So we are talking about thin disks that are much younger, but they are not very young. Good. And when we extracted the star formation histories of the different regions of this galaxy, actually this is on the, yes, okay, good. It appeared, but then disappeared again. Yes. Okay. Good. So just yeah, going back to the map. So we found in this galaxy this old metal poor alpha-enhanced thick disk, and when we extracted the star formation history of the thick disks in a similar way to what I showed earlier for the lenticular galaxies, we also found that we had a main very old component, but then a little bump here, a bit younger. And we analyzed the distribution of metallicity and ages of the stars as fitted by PPXF. And we found that actually the main component is this blob here. And so, yeah, it is very old with an average lower metallicity. It has some chemical evolution. But at a certain point, so for ages between 8 and 10 gigayears, we have somehow a bimodality. So here the higher mass fraction is blue and the lower is yellow. So it is higher in the green, in these two green regions, here and here. And this means that we have a bimodality in metallicity for the same, for similar ages. And also the way to explain this, to explain the fact that at the same time, in the same cosmic time, we can form stars that are more metal rich on the one side and more metal poor on the other side, is that the metal poor component was formed in lower mass galaxy, which was later accreted. So yeah, we kind of found this pattern also in this galaxy, which is an SB galaxy, which is very massive. So now when we found this, the question was, okay, but do we find this for all galaxies? What happens when we go to the part of the Hubble sequence with the latest type galaxies? And so now we'll show a very different sample. This is a sample of 8 adjunct galaxies that was for which Muse data were released by Sebastian Comenon et al. In 2019. We show their kinematics in a second. And of these galaxies, 5 of them have a clear double disk structure. Well, 3 of them have only single disk. So this was the work from my former student at the University of Heidelberg, Natasha Sattler. This was actually her master thesis, and she has submitted a paper recently, which is already in the archive if you're curious to check it. So yeah, here we are moving a bit more to the right of the Hubble sequence, because these galaxies are actually very dusty, start forming. They have lower masses, and they actually have some ionized gas, which is extraplanar, even in the heights corresponding to the thick disk. If you look at the position of this sample in this diagram, which is star formation rate as function of the galaxy mass, this is from Rocho et al. 2022. The sample is here. So the 5 galaxies with the thick and thin disks are located here. And here I added the mass range of the lenticular galaxies, which were very quiescent. They don't have star formation at all. Just to show you that we are not very different masses, but a little bit lower masses, but they were quiescent galaxies in this sample here. We have very star-forming galaxies. So very different sample from the lenticular galaxies. And if we compare to the other massive SB galaxy, which is NGC TD746, this is a Green Valley galaxy, so for its mass not strongly star-forming, and a very different mass, which is much higher than the sample that we are going to talk about now. So yeah, let's see what we find with this very different sample. This is the kinematics from Comenon et al., which was published in 2019, where they found the kinematics didn't need any large fractions of retrograde material to explain the observations of these kinematics. The author said that the results were compatible with some accreted stars, but not a large fraction. And when we extracted the star formation, the stellar populations of these galaxies, we found actually something very interesting. So this is, in the top panels, the age, and in bottom panels, the metallicity of the different galaxies, each one in each column. And where I'm showing here the transition between the thin and thick disk in this gray, with these gray horizontal lines. I hope you can see them from there far away. And so here in this color scale of ages, we see that we are talking about ages that are completely offset from the ages that I've been showing earlier. If you remember, we found galaxies with thick disks which were very old, so older than 10 gigayears, and the thin disks were 4, 6 gigayear old. So in general, these galaxies are much younger, and they are also much more metal poor. So we don't see actually very metal-rich thin disks as we found in the previous galaxies. This is somehow something that we would expect, because from galaxy evolution, we know that galaxies in the right side of the Hubble sequence, so the latest types of these galaxies, we tend to have younger ages when we talk about these galaxies, and lower metallicities. But here the interesting thing is that we find relatively young ages also in the thick disks. So the thick disks here are more or less between 3, 4, 5 gigayears. And these are the ages that corresponding to the thin disks in the galaxies that I showed earlier. Yes, and yeah, again, we don't find this very metal-rich thin disk that we found in the previous galaxies. When we extract the star formation histories of the thick disks in these galaxies, we also found something very different. If you remember, the star formation histories that I showed earlier were kind of truncated here with a very strong component and very odd ages here. And here actually so in these galaxies, at the ages where the star formation histories were truncated in the previous galaxies, so something like this. So at the same ages, these galaxies are actually forming most of the mass in the thick disk, so between 7, 8, 9 gigayears. Another important thing is that the star formation histories here are extended. They are extended to relatively recent times. And these two things, these two factors combined together, make these thick disks actually relatively young. So for these galaxies, we cannot believe that we had an early fast formation high redshift. We don't find any hints of that, but instead of a slow, probably in situ formation of thick disks, so across time in a slow way. Yes, so far we have found, I've shown hints of the dependence of the differences in the thick disk properties. I mentioned the stellar mass, I mentioned star formation rate, morphological type. However, I've been showing so far individual galaxies or small samples, because we didn't have until now like a systematic study of a large sample of galaxies, allowing us to study trends with the stellar mass or the star formation rate of the morphological type. And this is because the observations of thick disks are quite challenging. They are faint, and we need very deep observations with long integration times for to be able to extract the stellar population properties. So with the need of a systematic study with a larger sample, we got time for a large program with MUSE, which is the Gecko survey, which is still with the observations ongoing, and which is targeting 35 adjoint Milky Way-mass galaxies. With deep MUSE data, which is important and ideal to study the stellar population properties of thick disks. So this is the sample of the 35 galaxies. So we have some variety in the morphologies and colors and so on. But so the sample is built up on Milky Way mass galaxies. So we have a small range of masses around the mass of the Milky Way. You can see them mass range is relatively small, but we have a large variety of different star formation rates. So here we have an excellent opportunity to study the trends of the thin lattice properties with the star formation rates, because we are kind of removing the dependence with the mass, which was one of the potential other factors affecting the stellar populations. This is the same thing, but just with the points of the single galaxy. So just to show, this is the Milky Way. So around the Milky Way mass, we have galaxies that are above, within, and below the star formation main sequence of galaxies. So variety of star formation rates. So now we show a subsample, so the first results of a subsample of 6 galaxies for which we have fully reduced data, and for which we know from previous morphological decompositions that they have a clear double disk structure. So these are the galaxies. So we have also in these 6 galaxies some variety of the star formation rates. To feed these galaxies, I'm using the NGIST pipeline, which is an updated version of the previous GIST data analysis pipeline from Edge and Bittner that we have updated in geckos. And this also uses PPXF, so same code that I mentioned before. So in this analysis, I'm using the new SMILAS models, which actually allow for a better analysis of the alpha enhancement, because they offer 5 different values of magnesium over iron, not only 2. And with this, I'm extracting the stellar population properties. So here I'm showing again from from top to bottom age, metallicity, magnesium over iron. Sorry for the continuous change of the color scales, but I actually like very much this color scale for ages, because this helps our eyes to very quickly pick what is old, what is young, because so old ages are magenta and young ages are cyan. So again, I'm showing the transition between the thin and the thick disk with these horizontal lines. And I'm ordering galaxies in different columns from lower star formation rates on the left side, where we find the more quiescent galaxies, to the right side when we have higher star formation rates and therefore strong star forming galaxies. So the first thing we see is that we have, in general, older ages in the more quiescent galaxies, which makes a lot of sense by definition almost, because we have the predominantly magenta colors. And on the right side, in star forming galaxies, we have somehow, I lost the cursor, okay, it's here. We have much younger stars. But again, the interesting thing is that this trend, we have it also in the thick disk. And we find that the edges in the left side of this slide actually reminds us more the first galaxies that I showed at the beginning of the talk. So these lenticular galaxies and that massive SB galaxy, because in more quiescent galaxies we actually find old thick disks. But this doesn't happen in more star-forming galaxies, which kind of remind us more the last sample that I showed, with these very late type galaxies with strong star formation and with younger ages. For the chemical composition, so metallicity and magnesium over iron, we see clear differences between the thin and the thick disk only in the galaxies that are more quiescent, where we see a clearly metal-rich thin disk and the thick disk which is metal-poor, and which is also alpha-enhanced in contrast to the thin disk. And these differences are kind of lost in the latest type, in the galaxies with the highest star formation rates. So we can also summarize this in this kind of plots. So this is just the thick disk properties. From the left to right, we have age, metallicity, magnesium over iron as function of the star formation rate. So we will have the more quiescent galaxies in the bottom region of the diagram of the plots, and in the top region we will have the most star-forming galaxies. So for the metallicity, we don't find any clear trend. We find just the scattered points. But for ages and magnesium over iron, we clearly see that in this gecko sample, we have in the more quiescent galaxies thick disks that are very old, and they are alpha enhanced here. This doesn't happen in the star-forming galaxies, in the strongly star-forming galaxies, where we don't have this enhancement, and where the thick disks are actually much younger. So this sample, trying to reconnect this sample then with the results they showed earlier, it looks like there is a trend with the star formation rate in the stellar population properties, and therefore in the formation processes that led to the formation of thick disks, with more quiescent galaxies suggesting fast formation high redshift, with these like prototypical thick disks, which are old, metal poor, and alpha enhanced. But this doesn't happen in the most star-forming galaxies, where we have results which suggest the slow extent formation across time. Nice. So now, very quickly, I would like to show you one single disk galaxy. We have some of them, but I will show one representative example. So this is one galaxy of those that when we fit the vertical surface brightness profiles, we fit them better with one component than with two components. So a single disk galaxy morphologically. NGC 3501, this is a very late type galaxy, and this was the work done by the same student that I mentioned before, Natasha Sartre. This was her bachelor thesis, and she published a paper last year about this. So yeah, a single disk galaxy for which we didn't expect to find like sharp differences or clear differences in the stellar population properties. Because if you have a single disk, you would expect to have like a smooth behavior also in the stellar population maps. However, when we extract the stellar population maps, so here I will focus on metallicity. This is the metallicity, but if you're curious, we have also age and magnitude variant. I can show you later if you're curious about it. But the metallicity is very clear to see that this galaxy actually has structures, different structures in the stellar population properties. So in general, it is a young galaxy. So in the early stages of its evolution, which fits very well, you know, in the galaxy evolution models, which very late type galaxies kind of evolve in a slower way. And when we look at the metallicity, however, we see that there is like a thicker metal poor structure. So the galaxy is in general metal poor, which also fits in that same idea that this type of galaxies also have like a slower chemical evolution. But there is something else here, because apart from the thicker structure, which is metal poor, we do see like a thinner, a much thinner metal-rich disk, which is grown here in the center. So this is probably a thin disk in the first stages of formation. We don't know if in the future we will keep growing this thin disk in an inside-out way, and therefore we will have a massive thin disk. But in any case, we do have here a thinner metal-rich rotating structure, which is formed here in the inner region of the galaxy. Which is also these results are actually supporting the idea that this kind of galaxies, apart from having a lower evolution, this also happens in their thick and thin disk, and that galaxies form first like a thicker structure and then later on a thinner structure. And this galaxy probably didn't have time yet to fully form a thin disk, which is starting to form here just in the inner region. Good. So this is all we have so far from observations from intergraphy spectroscopy. We have to wait a bit more for the next GECOS results, where we will be able to show the 35 galaxies. But so far, we can also compare to simulations to get some more hints about the formation of thick disks. Because in simulations, we can have large samples. We don't have the observational limitations. We can also travel to the past, and we can label the stellar particles and see, so identify them according to their in-situ or ex-situ origin, for example. So I analyzed also a sample of zoom-in cosmological simulations from the AURIGA suite. So I selected a subsample of 24 galaxies. The AURIGA zoom-in cosmological simulations are all Milky Way-mass, and they are all relatively isolated at redshift 0. So I projected all these galaxies edge-on, so to be qualitatively at least comparable to observations. And I actually perform the morphological decomposition into a thin and thick disk in the same way as we do for observations. So I projected all the stellar population properties in job maps, so to have also something that could be qualitatively comparable to observations. So I have the maps for age, metallicity, magnesium ovarium for the 24 galaxies, but I will focus here on only 2 of them, which are some representative galaxies that I would like to use to reconnect to what we found in observations. So yeah, from the left to the right, I'm showing here age, metallicity, magnesium ovarium of 2 galaxies. So in the top panels, we have AU7, which is a galaxy with a relatively young thick disk, and another galaxy, AU18, which has like the prototypical thick disk with old, metal poor, and alpha enhanced stars. So in simulations, we have the opportunity to analyze the properties, but also to go back in time and understand a little bit better how we got these properties. So what is the process that led to these stellar population properties? So if we go back in time, we can plot different snapshots of the simulations. So here I'm showing snapshots from high redshift to low redshift from top to bottom. This is actually redshift 0. And I'm showing on the left side the surface brightness and the right side the metallicity. So this galaxy, very early times, is very small. The mass is very low, so it had a kind of a slow evolution at the beginning. So 10 gigayears ago, this galaxy is very small. It started to have somehow a thick rotating structure, but yeah, very small. And from that time on, it has a very intense phase of mergers, which help it to grow in mass. I will go back to this in a second. And only after the merger phase, so here, so the merger basically ended after 4 gigayears ago, so very recent times. Only after that, we could form a thin disk in the midplane. So like the gas was able to cool down and form a structure which was thin. For the other galaxy, the picture is very different. So you can see from the beginning, it has a much faster evolution. So 10 gigayears ago, it actually has half of the mass formed, and it has a thin and a thick disk already in place. From the time on, this galaxy just evolves and keeps growing, especially the thin disk, which is growing inside out. You can see this is the metallic stars are concentrated in the center at the beginning, but this grows inside out, and therefore the stars with this same metallicity are kind of growing from the center to the outskirts. So very different evolution. Furthermore, we can analyze in simulations the fraction of stars that were accreted and in situ. And so going back to this important merger phase in this galaxy, the satellite galaxies actually provided a significant mass to the galaxy. But in particular, in the thick disk, we have half of the mass which was accreted. So this thick disk is half formed in situ and half ex situ. And something very important is that these mergers also provided a large fraction of accreted gas, which fuels the late star formation, not only of the thin disk, but we also have recent star formation in the thick disk. And this kind of reminds us, you know, the extended star formation histories that I showed for some of the observed galaxies. So maybe gas accretion, because also gas accretion actually was some hints of gas accretions were found in some of the very late type galaxies that I showed from observations. So this is probably key to understand why we have younger and older thick disks. In the other galaxy, instead, we have low accretion fraction. And these thick disks, this thick disk in this galaxy basically is mostly formed in situ with only 7% of the stars which are accreted. So an in situ thick disk. Yes, so the idea of the gas accretion is very important to understand that probably this is how we form, how we can fuel the recent star formation also thick disk height. This is all I wanted to show you. So my take-home messages are mostly that thick disks are a complex structure that result from the combination of different processes that can be in situ and ex situ. So we probably have, in all cases, like a first primordial thick disk which is formed in situ, but then we have ex situ components that are more or less important depending on the galaxy, and with accretion of gas, which is which could be very important especially in some types of galaxies. In observations in particular, we have seen that thick disks are diverse. There is some diversity in the stellar population properties. They don't have to be necessarily very old. There are some relatively young thick disks, and this variety of properties actually suggests different formation histories with more quiescent galaxies, with the results that suggest a fast formation at early times, but with more star-forming galaxies, suggesting a slow extended formation across time. And this is all. Thank you very much.
Thank you, Francesca. Very nice talk. We have time for questions.
Thank you, Francesca, for your talk. Very interesting. I have two questions. The first one, I somewhat missed. How did you distinguish between the thin disk and the thick disk? If you could explain again.
Yes.
And the second one is, how reliable are the star formation rates that you infer? Because since you are considering edge-on galaxies with lots of dust along the line of sight, I suspect that you are estimating, I don't know, but a fraction of the actual star formation rate. How do you deal with this problem?
Okay, so for the first question, I can, if I manage to do it, I can, oh, it will take ages probably. Yeah, sorry about that, because I think it's much easier to understand this with a slide where I show the surface brightness profiles, which was this one. So basically, you take vertical surface brightness profiles, like for example this one. So in this study, concretely they just took different radial beams and they extracted different surface brightness profiles vertically. So this is Z here. So the observed points are, the observed profile is these black dots. And you fit this profile with two components, like for example, hyperbolic secant square, which is the most used. And you use one of the components with the largest scale height. And therefore, you find the regions where the thin disk dominates and the thick disk dominates. This is actually a very simple geometric definition. So from this, because these edge-on galaxies are just projected in the sky, and you cannot like reconstruct. It's very challenging to reconstruct the three-dimensional structure. So basically, you take the region where the thin disk dominates is your thin disk. So because you assume that the properties that you are finding here are basically the properties of the thin disk because it dominates. And same thing for the thick disk, where it starts to dominate. You assume that the properties that you have here are basically the property of the thick disk. Is it kind of clear now? So for the second question, that's a very good question that we should probably discuss in the GECKO's collaboration. I think you're probably right that if you have a lot of dust, you are missing some of the emission that is outside. So I'm not very expert on determination of star formation rates. This was done from H-alpha emission mostly. And I think this is something that we should discuss in GECKO's actually to, yeah, have an estimate. And in any case, here I'm showing kind of a qualitative trend with the star formation rate. So I guess that, you know, the exact values of star formation rates are not super important. What we are seeing here is that there is a trend, a difference between galaxies with the lower star formation rates, independently of the specific value, and the higher star formation rate. So I hope this is not too far from the truth, but yeah, definitely it's something that we should discuss. Thank you for the comments and the question.
Hi, thanks for the talk. I have a question about geckos. Those galaxies are selected in a specific environment?
This is also a very good question. So we didn't select galaxies for their environment. Actually, we didn't care about the environment. We just selected most of the galaxies that were bright enough with the Milky Way mass, with a variety of star formation rates. That because to do this, to get some signal to noise, you need to have these galaxies within a certain distance. So we selected the galaxies within 70 megaparsecs from us. So we didn't pay attention to the environment, basically. I know there are some group galaxies. This is probably one in the there is one in the Virgo cluster, and it's probably the only one in a cluster. But in general, they are mostly isolated galaxies. There are no galaxies with very strong distortions or signs of ongoing mergers.
Hi, very good talk. Thank you. I was wondering about getting the star formation histories from the same point, but based on the brightness and the mass of the stars. Have you tried, or how is PPX? I forgot how PPXF obtains the H's, but yeah, that's
from the brightness and the mass of the stars. You mean maybe resolving the individual stars, right?
No. If you see the total emission, you can say, okay, young stars will be more in the bright part. If you take for flux, you will retrieve the star formation history from young stars. And if you take the mass, you will take from the templates you use for PBXF, for example.
So with
you know how bright are them, and yeah, what is the mass of each of the templates. So you can obtain the star formation histories from young and old in the same region. And doing that, you can also get two patterns, like two star formation histories for the same points. What will happen then?
So we have done that. In principle, as far as I know, we use full spectral fitting because it kind of removes part of the degeneracy that you may have between age and metallicity. So that would be the reason why we use this method. But it would be something also to check.
Okay, thanks.
Hi, Francesca. Very nice talk. I am very curious about the galaxies that you mentioned that apparently have only one disk, which are the thick disk. So I have two quick questions about those. If we have a fraction of how many of, I don't know, the galaxies, the edge-on galaxies that we see have only one disk, and if you see those in the AURIGA simulations, because I'm curious why some galaxies would develop two and in some cases only one. Thanks.
Yes. So I'm not sure if we have a systematic study of galaxies in general to estimate a fraction, but I can tell you that from DS4G morphological decomposition, which was performed by Comeron et al. In 2018 paper, this is the paper from 2018, they analyzed more than 150 galaxies, more than 100 for sure, and they found that more than half of them, probably 60%, had two disks. But still, there were many, probably 30–40%, that had only one disk, which in this case means that either these galaxies are better fitted with only one component, or they use two components because the fit was better, but one of the components is dominating all over the height that they observed. Yeah. And you asked about the simulations. So in the AURIGA simulations that I analyzed, I only found one galaxy, which is a bit peculiar, for which the fit with one disk was better. This is a galaxy with a very recent massive merger, and you can see also in the stellar population maps there is basically no structure. Probably the thin disk was a bit messed up, and therefore morphological. I mean, when you use two different profiles, you cannot fit where one starts to dominate. We have also to be a bit careful when we compare simulations with observations, because simulations are very useful, but of course they are not, you know, the absolute truth. So it might be that we don't have certain types of galaxies in the simulations. And furthermore, these ones are cosmological, but they are zoom in and they are Milky Way-mass. So we are kind of limited. So it doesn't mean that we don't have them then in the real universe.
Yes, just a quick question following up. Hi, Francesca. When you have two components, you'd separate thin disk and thick disk through the scale height of the components that you find. But then when you find only one component, why do you call it thick disk only? Can it be only thin disk, for example? Is there a limit on the height that we can call one or the other?
No, I think there is no universal definition, so I don't actually call it thick disk. In the galaxy that I showed, we do see, for example, in the metallicity, we have a thicker and a thinner structure. But yeah, actually, in that galaxy, the thicker structure is not very different from the thin disk in the Milky Way in terms of scale height. So yeah, I think here we have thicker and thinner. We don't have a universal definition of what is thick and what is thin. And in high redshift galaxies, they compare single disks with the thick and the thin disks in galaxies a similar redshift with two components. So it's also relative. Yeah.
Francesca, several of the galaxies we have observed in geckos have boxy peanuts, or even an X-shaped bulge. So these structures are expected to be the central part of the stellar bar, and these bars are expected to move the gas towards the center. So can we expect to see some relation between these extended episodes of star formation in the thick disk with the presence of the boxy peanuts?
I would say yes, but I don't think we have any hints at the moment or any specific, you know, sign of that in this data. Yeah. Also in the maps that they showed from geckos, we don't see clearly the box peanut in the stellar population. So yeah, I would say yes, but we don't know, in fact. Yeah.
More questions? Thank you again, Francesca.